In this session, we will discuss a very important subject that's considered by many statisticians as the backbone of statistics. This is the subject of probability. Probability is a fundamental part of our life. We use probability all the time in expressing so many things. Experts in different fields, they rely on probability in many applications, as we will see by examples very shortly. This session is one of 3 or 4 sessions in which we will go over different aspects of probability. We will begin by discussion of the theory of probability, the classic theory of probability. We will then move into the discussion of empirical probability, which is a very important subject, especially in different applications. We will then in later sessions talk about probability distributions. We will talk about discrete variables and the probability distributions used for discrete variables, as well as probability distributions used for continuous variables. And as we will see, that understanding probability will give you a good idea about what statistics is all about. It's relying on past events, looking at patterns and hoping to establish some probability of the chance of things to occur in the future. In that sense, as I said, probability is considered as the foundation or the backbone of statistics. With that, let us begin our first session of probability. Let's go to the slides. Probability in life. As you watch the news every day, you hear forecasters saying that there is a 70% chance of rain tomorrow. That's one way to describe probability of some form. As you plan to enter a new business, an expert in the field tells you about the probability of making a first-year profit in this business is only 0.4, or there is a 40% chance that you will make a profit. Obviously, you will then have to make a decision whether you want to enter this business or not at this very high chance of risk or relatively low chance of making profit. As you take a new course, you may be wondering about the likelihood of passing or failing the course. If you know that 80% of the students pass the course, then that's an 80% chance of you passing the course, provided that your performance will be as good as the 80% of the students. You hear it on health news all the time that a smoker has a much greater chance of getting lung cancer than a non-smoker does. So as you can see, probability is used in many different forms and many different ways in life, and for that we have to address probability, and we have to understand the fundamental concepts of probability. It's very important first that we define some of the common terms that we will use throughout the discussion of the probability subject. The first term is what we call an experiment. It's a very common term that many people use. It's a pre-planned process for the sake of producing data that can reveal the purpose of the process application or meet the objectives of the study in which the experiment is conducted. In the context of probability, when the term experiment is used, it typically indicates a process that can result in only one of many outcomes. So we have to keep in mind that we use the term experiment in probability because we are interested in one of many outcomes and the chance of this outcome to occur. Speaking of outcomes, the next term is an outcome, which is obviously the result of an experiment. And when we discuss or when we talk about outcome, we are talking about a single output or a single outcome of the experiment, as compared to an event, which is a collection of one or more outcomes of an experiment. These are fundamental terms that we have to use all the time in probability: experiment, an outcome, and an event. The other term, which is extremely important, is the so-called sample space. A sample space is all possible outcomes taken together from an experiment. So when we can display all the possible outcomes of an experiment, that is what we will describe as a sample space. Here is, by example, we rolling 2 dice, and as you can see, there are in this experiment many outcomes that can happen, many events that can possibly occur, and an outcome, for example, may be 1 and 1, meaning the 6 and 3, as you can see here, or 1 and 2, 1 and 3, and so on. Now, if you're looking at an event, that event may be the odd sum or the even sum, which will be 2 and 2 or 2 and 4 and so on. These are all events which, as you can see, they represent collections of outcomes. What you see here in the bottom of the screen is the entire sample space of an experiment of rolling 2 dice. So that's what we mean by sample space. These are all the possible outcomes. Ways to display events. There are common ways in probability to display events. One of them is the so-called the Venn diagram, and the other is the tree diagram. In the Venn diagram, as you can see here, the S implies the sample space. That is all the possible outcomes. So if we are tossing a coin, for example, all possible outcomes will be head and tail. And you can see that they are represented by circles inside that square or rectangle, which represent the sample space. A tree diagram, on the other hand, is branches describing the progressive change in the experiment. So if the experiment is only tossing a coin, then the 2 outcomes that can possibly happen are the head and the tail, as you can see here. We will use these later on in many examples. Here is an example. Display the tree diagram of the experiment of tossing a coin twice. Now, tossing a coin twice would involve 4 outcomes. Head and head is 1 outcome. Tail and tail, head and tail, and tail and head. Now, these 4 outcomes are represented by the sample space. So S here represent the sample space, and the set that we are putting all the outcomes in is the set of sample space. Now, in a tree diagram, we start progressively by the first outcome. It can be either a head or a tail. If a head happened, then the next outcome is likely to be, again, a head or tail. If the first toss resulted in a tail, then the next outcome is likely to be a head or tail again. So what we have here is combinations of outcomes leading to events that are HH, the head and head and tail and head, and tail and tail. So you can see that the tree diagram has helped us in illustrating or displaying the events as they come. And you can imagine how useful this is if we are talking about a more complex experiment in which perhaps 4 coins or more are being tossed, and we are looking into all the combinations of events. A tree diagram represents a simple display, graphical display that is, of all the outcomes, and at the very end you will see the entire sample space as being the outcome of the tree diagram. It's also important that we understand what we call mutually exclusive events. When events are mutually exclusive, this means that the occurrence of one event results in other events not to occur at the same time. If you are, for example, tossing a coin, then it's either head or tail, and the occurrence of a head will prevent a tail from happening. So we call these mutually exclusive events. When we inspect the items for shipping in a manufacturing environment, the item can be either good or bad. It can pass or fail. And these are all mutually exclusive events. There is also the collectively exhaustive events. Other events that are called collectively exhaustive events imply that at least one of the events must occur when an experiment is conducted. For example, if we're speaking of rolling a dice, then we have 6 possible outcomes, and in any outcome would be either odd or even. So that makes these events collectively exhaustive. Back to fundamentals. What is probability? Well, probability is a numerical index of the likelihood or the chance that a certain event will occur. Typically, it's a value between 0 and 1, which reveals the relative possibility an event will occur. When a probability is 0 or close to 0, this implies that an event is very improbable to occur, or the chance of occurring this event will be very slim or very small. On the other hand, if p equal 1, then there is a high assurance that an event will occur. So these are our extremes. P is 0 is the low probability side, and P is 1 is the maximum or high probability side. It's also very important that we think of probability from the category of probability that we are dealing with. In this regard, conceptually, there are 2 main types of probability: objective probability and subjective probability. Objective probability is typically based on the relative possibility of occurrence of an event, defined either by the classic law of probability or by using empirical means, as we will discuss shortly. Subjective probability, on the other hand, is revealed from personal judgment, expert opinion, some information. It doesn't rely much on data or numbers, but rather on some form of expert opinion, perhaps, or personal judgment, or perhaps a desire or a wishful thinking, such as when a student say that there is a 90% chance that I will pass this test. Maybe this student is relying on her past performance, but there is no guarantee, and there is no data to support that the chance of her passing this particular course is 90%. When people claim that they know something, it gives a very pleasant feeling sometimes, especially if it turns out that they are right. So subjective probability is a common part of probability that's used by many people around the world, and we have to be very careful whether the people that are expressing a chance or probability are relying on data and facts, or they simply expressing personal judgment or expert opinion, or perhaps some information that they know that we don't know. That takes us to objective probability, which is really the core of this session here. Classic probability, or the classic theory of probability, is the foundation for probability. It's very simple, because the classic probability of an event, A, is determined by the ratio between the number of favorable outcomes, M, and the total number of possible outcomes, N. So it's M over N, and we express it, as you can see here, that PA, or the probability of the event A, is equal to a ratio, or the ratio between the number of favorable outcomes divided by the number of total outcomes, or the total number of outcomes. In tossing a coin, for example, a total outcome is 2, head and tail. So if the interest is the probability of head or the probability of tail, then it will be 1 divided by 2, and it will be 1/2. That is the classic definition of probability. Now we have to also understand that the probability of non-occurrence of the event A, or the complementary probability, is called the probability of failure. So probability of success will be A, probability of failure will be expressed as PA dash or P not A. In some books they will use the symbol Q to express the opposite probability. And as you can see here, since the sum of probability is 1, then the probability of not A, or the QA, will be 1 minus PA, or 1 minus M over N, in comparison with the probability A. So we need to understand that. Given the fact that the sum of probability is 1, then if we know the probability of some event to occur, we will know the probability of some event not to occur, which is 1 minus the probability of the occurrence of the event. In summary, classic probability is based on the definition PA, or the probability of A, which is the number of favorable outcomes M divided by the number of outcomes, total number of outcomes N. And any probability will have to be of any value from 0 to 1. It cannot be negative, and it cannot exceed 1. So the minimum is absolute 0, and the maximum is absolute 1. The sum of probabilities in a given experiment is always 1. So these are the 3 basic rules of probability. PA, M over N, probability range from 0 to 1, and the sum of probabilities equal 1. Let's take an example here. In an experiment of rolling a die, find the probability of obtaining an odd number in one roll of a die. Well, we know that if we roll a die, we will have 6 outcomes. 1, 2, 3, 4, 5, 6. So the probability of obtaining an odd number, we need to first observe how many odd numbers we'll have. And these are the 1, the 3, and the 5. So now we have the favorable outcomes are 3, which are the odd numbers. But the total number of possible outcomes is 6. So 3 divided by 6, by the classic definition of probability, will give us the probability of interest. That is M over N equals 3 divided by 6, which would be 1/2. In an experiment of rolling a die, find the probability of obtaining a number less than 4. Now, a number less than 4 can either be 1, 2, and 3. These are the 3 numbers in rolling a die that will be less than 4. And again, these are the favorable outcomes, the outcome that we are interested in. So if we divide the number of these outcome or favorable outcome by the total number of outcomes, that will give us again the probability of obtaining a number less than 4. And as you can see here, we can either take each one of them individually. We can say 1 over 6, 1 over 6, and 1 over 6, and that will give us 3 over 6. Or we can say that since we have 3 outcomes out of 5, then that would be 3 over out of 6. I'm sorry, that would be 3 over 6, and that will give us 1/2. In the experiment of rolling a pair of ordinary dice, answer the following questions. What is the probability that both dice have the same face? Now, here is the sample space of rolling 2 dice or 1 die twice. And as you can see, we have 36 outcomes. So the number of total outcomes or all possible outcomes is 36. But what we are interested in is the same face. Well, same face would mean 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So we have 6 outcomes or 6 favorable outcomes. If we divide these by the total number of outcomes, which is 36, then that will give us the probability that both dice show the same face. As you can see here, 6 divided by 36, or 0.167, is the probability of the event of interest. Another example, what's the probability that the sum of 4 are rolled for the same experiment, or that both dice come up with a sum of 4? Sum of 4 would mean 1 and 3, 2 and 2, and 3 and 1. And again, these are 3 favorable outcomes out of the 36. So 3 divided by 36 is 1 over 12, or 0.083, which is the probability of interest. In the sample space below, what is the probability of the two faces will have different numbers? Now, again, different numbers means 1 and 2, 1 and 3, 2 and 3. Early on, we were able to get the probability of same numbers, or same faces: 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So if we know the probability of the two faces being the same, we can easily, instead of counting all the events in which we have different faces, we can easily use the complementary probability, or since 6 over 36 is the probability of the two faces being equal, then the probability of the two faces being different will be 1 minus the 3 over 36. That is taking advantage of the fact that the sum of probability is 1. So 1 minus 6 over 36, or 1 minus PA, will give us the PA dash, or the probability of two faces not to be equal, or the probability of faces being different. We will stop at empirical probability in this session, and in the next session we will talk about empirical probability, and this will be a different view of probability that I'm sure you will be interested in understanding.
Okay, we're good. That was a solid 20 minutes, right?
Okay, good.
Yeah, he was counting. He had.
You may start anytime.
Okay. In the previous session, we discussed the classic law of probability, and in the classic law of probability, we learned that all possible outcomes are typically well defined, meaning we know the entire sample space. So as a result, the classic law probability, defined as the number of favorable outcomes divided by the total number of outcomes, should give us specific and well-defined values. When we say the chance of head or tail in tossing a coin is 1/2, this is because we have two possible outcomes, and if it is the chance of head or tail, that's 1/2. Similarly, when we say that the chance of 1 or 2 or 3 in rolling a die one time, we have 6 outcomes. So that's the total number of outcomes, and the probability of any outcome, 1 or 2 or 3, would be 1 over 6. So we have a well-defined values of the total number of possible outcomes, as well as the number of outcomes of interest. Even when we went to a more complicated experiments such as rolling dice twice or 3 or 4 times, again we still have a well-defined number of total possible outcomes, and if we know the number of favorable outcomes, then the classic law of probability is very much straightforward. It's a ratio between the number of favorable outcomes divided by the total number of possible outcomes. We also learned that the sum of probability is always 1. We also know that the probability can range from a value of 0, which is the least, to a value of 1, which is the highest probability that one can have. Now we're moving on to another subject, which is the empirical probability. And to just give you an idea about what empirical probability means, we all know that the chance of head or tail in tossing a coin is 1/2. And 1/2 means